is Devin, and today we're going to be talking about numerical integration 2. Part 2 to numerical integration 1, of course. So, quick review. There are two types of common integrals. Definite integrals, which have factors of integration, for instance, limits of integration. For instance, 0 to 1 f of x dx. These result in a number. And indefinite integrals with no limits, just as integral f of x dx, those result in a formula. Now, what is that number of a definite integral? Well, it's the area under the function, of the curve of the function. So if we were to draw a graph here, and we draw a curve, right, let's say this curve is the function of f of x. So for the problem, say the integral of a to b f of x dx would be this. If a were here and b were here, then the solution to this integral is all of this area right here. Now, how do we find that? Well, we can approximate by using little rectangles like so. We'll just draw these like so. And we can use these rectangles to approximate. And these distances could be x1, x2, x3, b could be x4, and so on. Now, again, to generally find out the area, we take the sum of the area of all these rectangles, and that is the area. Now, we can use a formula to approximate this. If we draw out the integral, a b f of x, we could generally approximate this, that's what this symbol is, by taking the area of all of these. So we could do f of x1 delta x plus f of x2 delta x plus f of x3 delta x, and we have one more, so we have to do, actually no we don't. Yeah, we don't. Okay. So now, for instance, we could figure out generally what this is. Now we need the function for this. So generally, let's say the function was x squared. So that would make this. This is, x1 is, yeah, we could represent these by maybe 2, 3, and 4. So we could do f of 2 delta x plus f of 3 delta x plus f of 4 delta x, and then we do the math. So that would be 4 times, delta x is the distance between these, so all of these are 1. So it's 4 times 1 plus 9 times 1 plus 16 times 1, which all in all is 29, which is pretty close. But if we were to do something, say, like take the rectangles and make them even smaller, like if I were to draw another graph here, and we did rectangles more like this, don't want to draw them all because there's a lot of rectangles. But if we did something like this, it'd take a lot longer to calculate, but we'd get a lot, and I mean a lot closer to our result. So next, before we move on to our true main topic of the video, another quick review on partial sums. So if we have a sequence that's adding or subtracting, so for instance 1, 2, 3, 4, etc., that is known as an arithmetic sequence. And if it's multiplying, like for instance 1, 2, 4, 8, 16, then it's a geometric sequence. Now, what we can do is, we're going to basically square each one in this sequence. So we have 1 squared, 2 squared, 3 squared, 4 squared, etc. How would we figure out what our equation for this one is? For this one right here, this counting one, the solution for the sum, S of n, the solution for the sum of all of them is n times n plus 1 over 2. Now, how would we figure out the sum for this sequence? Well, I'm going to tell you the answer now, and we'll prove it a little bit. It's 2n minus 1 over 3 times n plus 1 over 3. Or, over 2, my bad. Now, if we were to triple it, for 1 cubed, 2 cubed, 3 cubed, the answer would be n times n plus 1 over 2 squared. So square everything. And that's how we find that. Now, we're going to prove how to do the square one. We'll do the cubed one probably in another video. So now to find the proof of the sum of the squares. So as a quick warm-up proof, let's review how we got our first formula. The sum of all numbers added, so 1 plus 2 plus 3 all the way to n. How is that n times n plus 1 over 2? Well, I'll show you. If, for instance, we had 1 plus 2 plus 3. Let's just start with s of 3. How would we get there? So let's draw this out. So we'll have 3 boxes, or we'll have 6 boxes. So we'll have 1, 2, and we'll draw 3 for 3. Now, what we can do is we can take this and we can flip it on its end. So, like, put it on top of this. So we'll represent those by asterisks, because I don't want to draw more boxes. So we'll do asterisk, 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 and asterisk, like this. Now, you'll notice this is a 3 by 4 rectangle, and we have double of what we need. So what we can do is we can do 3 times 4 and have it to find out how many this is. So that would be 3 times 4 over 2, which is 6. Now you're starting to see where this comes in. So if we were to do this with n number of boxes, so let's do 1, 2, and 3, all the way to n. We'll do n as 3 as well, because it doesn't really matter. How would we figure this out? Well, we'd have to take the entire thing and flip it on its side. So we have the exact same thing as our other example. And then however many n is plus 1. Because no matter how you flip it, this box right here would always be on top of the last one of n. So we would have our length of n and n plus 1. We divide it by 2, and there's our formula. N times n plus 1, for the entire thing, divided by 2 to get half of what we need. Now, let's move on to the triples. Now, the squared. Now, before we go too into this, I want to point something out real fast. We can draw a box of 4 by 4 squares. I'm going to draw this real quick. There you go, and then we go across, 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 and across. And we have a 4 by 4 of squares. Now what we can do is we can color these by box. So we can, for instance, have, if we build on this, we can have 1 red box, 3 green boxes, and we can just add a layer each time. So then we'll have 3 green ones, 5 blue ones, we'll said 6, and 7 black ones. Like so. Alright. So now notice, there's 1 of these, 3 of these, like I already pointed out, 5 of these, and 7 of these. Now if we add these all up, notice we get 16, which is expected. But we can also use this to help us. Now notice each time it increases by an odd number, and if we add any 2 adjacent numbers, or if we add all the numbers up to that point, is always a perfect square. 4 boxes, 9 boxes, and 16 boxes. Now for any number in this sequence, an, we could use 2n minus 1. That's how you get an odd number. So, yeah, just going to point that out before we start. Now, how would we actually get this formula? Well, let's do it. And in order to do this, we're going to need to draw a lot of boxes. And I mean a lot of boxes. So we'll draw one singular box up here by itself. We'll draw a group of 4 boxes right here below it. Forgot the middle line, my bad. Literally bad. We'll have 3 boxes, 3 by 3, right below that. Like so. I think the fastest I've ever drawn boxes in my life. 3 by 3. And a 4 by 4. That was too big, wasn't it? Nope, that was perfect. Okay. We go 1, 2, 3, 4, and 5. Like so. We can color these like before, adding a layer each time. So we'll always have our top right box of all of these be red, because we're essentially adding on to the next row of boxes. So our first one is red, then we add a ring of greens to make it another perfect square, which is 4, because 1 is a perfect square, 1 times 1. We'll have that. Then we add another layer, this time of blue. Oh, I forgot to add the green layer for all of these. My bad. Then we can add another layer of blue, another ring, to make it another perfect square. 9, by adding another 5. Do that for our last 2 boxes. Then we can add one more final box to make it another perfect square, 16. All these are going to be perfect squares because, again, if you'll think back to our sequence, we had 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, and 4 squared, which is 16, adding up to each of these amounts. Now what we're going to do is we're going to create a pyramid using these boxes. We're going to take all of these and we're going to turn it into a pyramid. So we're going to basically find the sum of these first 4. So we're going to make, I messed this up last time I did this, so I'm not going to mess this up again. That's 7, right? Yeah. We're going to have a row of all 7 blacks on the bottom. We're going to add another 2 rows of blue because there are 10 blues in total, 2 rows of 5. We're going to add 3 rows of green because there's 3 rows of 3 greens. And then we're going to add 4 reds at the very top. Because, as with the other colors, there's 4 reds. Excuse this little bit at the top, I messed that up. 3 and 4, and we have a pyramid. Now we just need to color it. So as I said, all 4 of these are going to be red. So we're basically taking all the reds and we're putting them on top. We're going to take our 9 greens, our 3 rows of green, and we're going to color all of these to help visualize. Color all of these. Our 2 rows of 5 blues, our 10 blues in total. And finally, our last row of 7 blacks. Okay, now remember how in our previous example, when we had the triangle and we flipped it so we could add to that, we flipped it and we added it, we had the stair of 3 and then we added it. We're going to do the same thing with this one, but the other way around. We're going to stack all 4 of these cubes together, and we're going to add all of them to the side of this. So we're going to add all 4 of these squares, which I'm going to try to draw to visualize, to one side, and another row of all 4 squares on this side, like so. And what we could do, like, we could color this, but this is going to take a very, very, very long time. But again, this would be red. Right here, this bit would be red. This square right here would be red, and the rest green. This square would be red, this square would be green, everything else blue, etc., etc. Now what we've done is we've made a rectangle. This is, in this case, a 9 by 10 rectangle. As you can see, this is a row of 4 reds, 3 greens, 2 blues, and 1 red, which adds up to 10. We have the 7 here, which we can use our 2n minus 1, 2 times 4 minus 1, which is 7, plus 1 plus 1. So that's 9. Now what we've done here, I'm going to do it this way. So we have 3 times what we want, which is 1 plus 4 plus 9 plus 16. 1 plus 4 plus 9 plus 16, which is equal to this. So we have our bottom row, which is 1 plus 2 times 4 minus 1, plus 1, like this, times this, which is just 1 plus 2 plus 3 plus 4, because that's 10. We have our 1 plus 2 plus 3 plus 4. Now, how do we generalize this? If this were to go on infinitely, there would be an infinite number of, I'm just going to, like, say if we repeated colors, there would be an infinite number of blacks in the bottom row, like wide, or depending on what n was. There could be as many as 100, there could be as little as 10, something like that. So we would have 3 times 1 plus 4 plus 9 plus 16 working down, 1 plus 4 plus 9 plus 16 working down, all the way to n squared, because these are all going to be squared, perfect squares, no matter what it is. Times our general, or equals our general statement of 1 plus 2n minus 1 plus 1, like so. And then this, it's just going to be 1 plus 2 plus 3 plus 4, all the way to n, because there's n squares, so there would be n, it would be n tall. Now, if we have triple of this, we can divide this, which gives us the generalization S of n. We divide everything by 3 equals 2n minus 1 over 3. That's how we get that. Times n times n plus 1 over 2. And that's our proof. Bye.